Before the universe was born, this topic is truly complex and mind-bending, but also strangely fascinating. We'll analyze it using existing theories. But honestly, when discussing the origin of the universe, it often goes beyond the realm of science, veering more into philosophical exploration. When talking about what was before the universe, you can't avoid the Big Bang. And the Big Bang wasn't actually an explosion. There was no bang. It wasn't a bomb, not an explosion or a fire. No explosion, no debris, no shrapnel. The universe was just smaller in the past and will be larger in the future. This isn't your only misconception about the Big Bang. The Big Bang didn't happen in any particular place. It happened everywhere. It wasn't an event in space, but an event of time. It was more like a tick of a clock than a mark on a ruler. It happened in the finite past of everything in the universe, every atom, every particle. Every point can trace its evolutionary origin back to the Big Bang. The Big Bang happened in the room you're in now, happened in the Andromeda Galaxy, happened within you, happened in every corner of the known and unknown cosmos. The universe has no center and no edge. It expands from nowhere into nowhere. The universe didn't originate from a point in space. The Big Bang is the origin of space. There's an inconsistency in these statements, a paradox. 13.787 billion years ago. Our theories tell us the universe, regardless of its size, even if infinite, was contained within a singularity, a point of infinite density and no spatial extent. But that doesn't make sense. It doesn't fit the rules of reason and logic. This is because the Big Bang singularity isn't a true representation of reality. It's just a heavy hint that our equations, our mathematics, and our physics are dysfunctional. The singularity is a marker of our ignorance about our origin. In that darkness of uncertainty, the seeds of new awakening are nurtured. For in our ignorance about the Big Bang, we have the chance to see the ghosts and whispers of relentless, complex mathematics pierce the veil of our origin, trying to infer what came before, because once there was no universe, and then there was. This is the mystery of creation, the paradox of our reality. There are inflationary explanations for existence, but was that beginning truly the beginning? Did time start with the Big Bang? Did our universe only come into existence at that moment? Or was there something similar before, or something completely different? If the Big Bang was the beginning of everything, is all we know also the beginning, or is our universe just a small piece of a grander story, a story told since distant past eras, and that will continue to exist after our universe sinks into cold oblivion? How did the idea of before the Big Bang even began to be discussed? This goes back to 2013. A celebration was held in the hall of the Paris Observatory. Participants congratulated each other on the mission's success. During the festivities, someone brought out crates filled with champagne from a back room. The icons on each bottle amazed everyone. On each bottle printed was an oval disc with a strange speckled pattern. This is the cosmic microwave background, CMB, a background radiation filling the entire universe. From shortly after the Big Bang, the European Space Agency's Planck satellite collected data. To construct this image, it was the highest resolution all-sky CMB image ever made. The party participants were celebrating the first public release of the Planck satellite data. They had every reason to celebrate the obtained data. The Planck satellite's data confirmed existing cosmological models and the Big Bang story. More importantly, it found evidence supporting the theory of inflation, that the very early universe underwent exponential growth in a brief moment. The name Big Bang we use, coined by astronomer Fred Hoyle, is really just a generic description of a cosmological model, where our universe was smaller in the past and will be larger in the future. In this model, there really is no explosive event that sparked cosmic creation or a resulting rapid unfurling of space. Everything we know, on the contrary, is much simpler, just an expansion from a small state to a large state. According to this theory, we can assign a number, 13.787, with an uncertainty of 0.02. It's a simple number, but this number is our current best estimate of the universe's age in billions of years. In fact, a direct consequence of Big Bang theory is that, before time, there was a moment when the universe simply came to be, 13.787 billion years ago. But as far as we know, this is only one dimension, time. The three dimensions of space that also constitute our universe might be infinite, yes. Our observable universe has a boundary set by the finite speed of light. This limit about 46.5 billion light-years away. We assume there's more universe, more stars, galaxies, gas, and dust, but we don't know what it's like, possibly infinite, but not in the direction of time. Our universe could live infinitely into the future. Even if our universe expands so far, so vast that all stars die out, existence is just a thin soup of particles at a temperature close to absolute zero. The universe still exists. Time still marches forward. Directions in space still exist, but the past is different. There is a boundary to our perception, a boundary to our understanding. Even if the universe is infinite and will extend forever into the future, it came asterisk from asterisk something. Now about the simple, straightforward Big Bang model. This simple, straightforward Big Bang model has been able to explain a vast amount of observational data, such as the apparent recession of galaxies away from us, the appearance of the cosmic microwave background, even the abundance of light elements in the universe. In fact, no other cosmological theory can explain the existence of all these facts. But like any other scientific theory or model, the Big Bang has its shortcomings. In 1979, physicist Alan Guth was studying a drawback in most theoretical models of the extremely early universe at the time. The universe seemed to naturally produce vast numbers of defects like magnetic monopoles, cosmic strings, and other exotic distortions of space and time. Yet these defects were never observed in the real universe, so Guth tried to find a way to get rid of them all at once. He proposed a new entity, something inhabiting the universe called a scalar field. In physics, scalar fields aren't a new concept. Quantum field theory, apart from Einstein's general relativity, is the foundation of our understanding of reality. Everything is fields. Every existing particle and every form of radiation is actually a manifestation of underlying quantum fields filling the universe. These quantum fields soak space and time, like olive oil and vinegar soak bread. Each particle has its own associated field, an electromagnetic field for photons, a Dirac field for electrons, etc. When these quantum fields are locally excited, a region of high energy, vibration, we see it as an individual particle. But of course, even if a patch of the universe contains no particles, the fields are still there. Scalar fields are the simplest type of field. They have only one value, a magnitude associated with each point in spacetime. Every time you see a weather forecast with a local temperature map, you're looking at a scalar field, a single number, in this case, temperature, associated with each point on the map. The eminent physicist Peter Higgs had already introduced the language of scalar fields decades earlier, when he proposed what's now called the Higgs field, a scalar field working in the background of spacetime, responsible for mass. Now it was Guth's turn to invent a new scalar field to fundamentally alter space-time dynamics in the distant past. This scalar field would permeate every corner of the early universe, then randomly, suddenly undergo a dramatic phase transition, collapsing into a lower energy state. This collapse would provide the necessary energy to make the infant universe much, much larger in an extremely short time. Guth estimated if the universe expanded by at least 1,050 times in less than a second, then all those troublesome defects would simply be diluted across the cosmos, far beyond our observable reach. The process of this rapid inflationary event would also solve two other challenges of the conventional Big Bang model, explaining why the universe, despite its vast volume, could have a uniform temperature. Because before inflation, the universe was uniform, and why it appears so flat. If you make any geometry very large, it always looks flat to any local observer, just as Earth looks flat in your garden. Therefore, because the concept of inflation so cleverly explained several features of the observed universe, cosmologists began taking it seriously within a few years. Guth's original idea evolved into the modern inflation concept, initially proposed independently by Andre Linde and the team of Andreas Albrecht with Paul Steinhardt. The quantum field didn't jump suddenly to a new state, but slowly evolved into a lower energy state. It was this slow roll inflation that was able to put the asterisk bang asterisk into the Big Bang. Initially, the inflation quantum field evolved into a lower energy state, powering the inflation. But at the end of inflation, when this field exhausted itself, the universe became large, cold, and empty. Yet here's the magic of slow-roll inflation. Through a process called reheating, at the end of inflation, the quantum field wouldn't come to rest at its minimum energy state. Like a ball rolling down a hill, the field would oscillate slightly. This oscillation transferred more energy back into the universe, not in the form of hyper-rapid accelerated expansion, but in the form of particle production, as understood in quantum theory. This allows quantum fields to constantly transform and mix. Thus, in its dying breath, the quantum field responsible for inflation decayed, filling the universe with all the particles of everyday existence. electrons, photons, neutrinos, and quarks, even dark matter, so if anything matches the popular conception of the Big Bang, it's inflation. Before that, the universe was small, hot, dense. When it was less than the tiniest fraction of a second old, yet within another tiniest fraction of a second, inflation activated, and the universe grew explosively. And at the end of that staggering inflation, the universe was re-energized, flooded with particles from the inflated field, particles that continue to inhabit the modern cosmos. But while this model conveniently explains many cosmological mysteries, it's not enough to elevate it to the status of major scientific theories like general relativity or germ theory of disease. It's not yet mature. Most importantly, when it comes to inflation, we have more questions than answers. We don't know the identity of the quantum field that drove it. Even if it survives to the present day, it's just a broken shadow, far beyond our detection capabilities. We also don't know why inflation lasted as long as it did, or why it had just the right evolution to trigger hyper-rapid expansion and then decay, flooding the universe with particles. Some cosmologists argue that due to these shortcomings, inflation isn't a robust scientific theory. However, the general concept of inflation, that a quantum field slowly evolves and triggers rapid expansion, followed by a deluge of particles, does make some testable generic predictions, and indeed they have been verified. Inflation's behavior not only rapidly expanded the universe, it also rapidly expanded the tiny quantum foam that fills space-time. Quantum foam is microscopic, existing at the lowest level of reality. The incredible expansion of the universe under inflation blew these foams into still very small, but absolutely larger variations than before. This formed the seeds of structure, tiny variations in space-time, led to gravitational differences everywhere over time. These differences grew, eventually becoming the grandest structures in the cosmos. Regardless of the precise mechanics of the model, inflation theory predicts that the cosmic structures we observe have very specific statistical properties, and the cleanest way to measure these structures is by mapping the cosmic microwave background, the leftover light from when the universe was only 380,000 years old. A major test of inflation involves the so-called scalar spectral index. Maps of the cosmic microwave background contain many blobs of various sizes representing cooler and hotter parts of the universe. Cosmologists can turn this map into a spectrum, measuring how many large fluctuations, how many medium, and how many small a scalar index of 1 would tell us. Fluctuations of each size contribute equally to the general pattern. Inflation models typically predict a scalar index slightly less than 1. In 2013, the Planck mission measured this number as 0.96. With 5 sigma precision, the Planck satellite measured the exact statistical properties predicted by inflation. This was certainly a cause for celebration. Thus, even though inflation sits at the edge of known physics, involving properties, forces, and fields most of us cosmologists don't yet understand, most cosmologists believe something like inflation happened in the early universe. Wow. There are other hypothetical alternatives to the inflation story. Ultimately, they all tend to operate in almost the same way. Rapid expansion of space, a deluge of particles, and the planting of the first seeds of structure. So even if inflation is proven incorrect by nature's theory, according to all available evidence, the universe at its earliest moments underwent something extraordinary, giving birth to the Big Bang, the never-ending bang. But if inflation is correct, if some exotic quantum field powered the hyper-rapid expansion of space and ignited the Big Bang, then this theory has some interesting implications. Because before the Big Bang there was inflation, and before inflation, from this perspective, driven by the cutting edge of theoretical physics, our perceived universe is just one in an infinite chain of universes, each universe bubbling up and branching from an endless stream that will last forever. Inflation would be eternal. Always has been, always will be. If this theory is correct, then what came before our universe hangs within our universe. In Fyodor Dostoevsky's 1846 novel The Double Asterisk, a struggling poem, a young bureaucrat finds an unlikely companion, a man who looks exactly like him. At first the two are friends, but then the double's charm starts taking over the original's life. Eventually, the original finds many copies of himself and is forced into an insane asylum. Though a fictional story, the concept behind it isn't as far-fetched as it seems, because somewhere in a distant galaxy, there might be a copy of you, wearing the same clothes, the same age, with the same life experiences, lovers, relatives, favorite restaurants, and hated sports teams. That copy would also bear your exact name. Might be watching a copy of this video simultaneously, both of you watching it at the exact same point, on an identical screen copy, hearing the exact same message, the same sounds. This copy would inhabit another universe, a universe so far away, it lies far beyond the observable boundary of our own, forever unreachable, forever unable to exchange information, but it could exist, a copy down to the subatomic level. This copy wouldn't be alone, farther than the nearest copy. There would be another, and another. In fact, there would be infinitely many, all watching this exact moment of this video. This is the reality of the infinite multiverse. A universe large enough contains infinitely many universes, large enough to contain every possibility, every combination of molecules, atoms, and subatomic particles, and replicates every possibility not just once, but infinitely many times, now and in the future. The concept of the multiverse is staggeringly vast, but its tantalizing possibility was born from the inflationary event before the Big Bang. One of the most vexing questions inflation itself brings is how it should stop to create conditions suitable for our universe. The quantum field powering inflation must slowly evolve to its minimum energy state and eventually come to rest. If the quantum field evolved too quickly, the universe would overinflate, making a life-filled universe impossible. The final state, called reheating, must also follow a specific path. Too much or too little energy injected would leave it barren. To cosmologists, this seems incredibly unlikely. A strange fine-tuning, a strange lucky coincidence. If the quantum field behaved any differently, even very slightly, our universe would just keep inflating rapidly, never slowing down, never resting, never filling with particles and fields, stars and galaxies. This is where the concept of eternal inflation comes from. In this model, once inflation starts in a baby universe, it continues forever. In the broadest sense, the entire cosmos constantly explodes, doubling itself in a never-ending, accelerating expansion spree. Like a race car driver who never lets off the throttle, the universe's inflation, once triggered in that first inflationary act, never knew how to slow down. But this does mean the universe has an ultimate beginning. Something must have kick-started the first quantum field to begin its journey toward inflation. So whatever universe had a finite age in the past, but it could live forever into the future. Another part of the cosmos would always undergo inflationary growth, and it would continue ad infinitum. Of course, we don't know if our universe, our inflation, our Big Bang was the first, if not, then before our inflationary event. What happened just a prior event, and one before that, and so on, back through the middles of time. But our observable universe obviously didn't experience this runaway growth. There's dark energy. Our universe is expanding at an accelerating rate, but compared to inflation, it's quite leisurely, not the kind of hyper-rapid expansion driven by an early quantum field. How do we reconcile this observational fact with the concept of never-ending inflation? To make this work, physicist and inflation theory pioneer Paul Steinhardt proposed, our universe is just a tiny bubble, just part of a much larger inflating space-time. In our little bubble, a portion of the quantum field driving inflation settled down, falling into a low-energy state. That local condition caused our universe to distinguish itself from the broader cosmos. Here, inflation ended. The part of the quantum field behind inflation decayed into the particles and radiation we see as the Big Bang. But outside the boundaries of our universe, the rest of space-time continues inflating. There, in the wider space-time, fragments of the quantum field keep separating. Each time they separate, a new universe is born with a new set of particles and forces, a new cosmic realization, of course. This proposed multiverse wouldn't be infinite, but would quickly approach possible scales. In just one inflationary event, our universe already grew 1,050 times larger than its observable volume. That's from an inflationary period lasting less than 10 to 30 seconds. Imagine if inflation lasted a full second, a minute, or 10 billion years. Who knows how long it's been since the initial spark. This is the inflationary multiverse, a vast, ever-growing collection of separate universes, each universe separated from the next by almost uncountable light years. This distance grows because inflation causes space to expand faster than light speed. Each bubble universe flies away from all others faster than light. No connection between them is possible. No communication, no influence. Surprisingly, it's possible, at least in principle, to test this idea. Even if other universes of the multiverse are unreachable, if our bubble universe collided with another in the distant past, that collision would appear to us as a circle in the sky, a ring formed by the intersection of our two bubbles. Many researchers have searched for these circles in modern cosmic galaxy maps and the cosmic microwave background. However, despite some intriguing hints, nothing so far has withstood further scrutiny. This lack of detection doesn't rule out the multiverse idea. Has the chance for our young universe to intersect with another is tiny anyway, but unfortunately, aside from this idea, there's actually no rigorous way to detect the existence of a multiverse, because by definition the rest of the inflating cosmos exists beyond our observable horizon, inaccessible. Because of this, many theoretical physicists condemn the multiverse idea, considering it not a valid scientific theory. In fact, this includes Paul Steinhardt himself. Despite being one of the originators of the eternal inflation idea, he later became an outspoken critic of all inflationary theories. All multiverses fail to explain anything about our particular universe. In a multiverse, every possibility, every arrangement, and every combination of particles and forces is possible. This means there is nothing special about the particular arrangement we find ourselves in, but there's also nothing special about any other arrangement. You simply can't tell from observations of your own universe whether a multiverse exists or not. This, unfortunately, is a very poor way to build scientific theory. Furthermore, currently, there's also no way to tell the potential variety of universes contained in a multiverse. The details would depend on the exact physical mechanism that initially drove inflation. In the simplest case, multiverse bubbles are just more universes with the same particles and forces just existing in different combinations. If we could visit another bubble universe, for example, we'd see familiar photons, electrons, quarks, etc. These particles would interact with the same forces we have here, so there would still be stars, galaxies, and cosmic webs, just in different patterns. But depending on inflation's dynamics, these universes could have different combinations of particles and forces, or even different fundamental constants. Different bubbly universes might have different speeds of light, or different electron masses, or no electrons at all. Most of the physics we take for granted could be completely different. Of course, most of these bubbly universes would be completely unsuitable for life or star formation, or even macrostructure formation. But with so many universes, everything gets a chance. This is one of the strange features of such a large multiverse, and for an infinite multiverse. Not only does each possibility appear once, each possibility appears a vast number of times. This means there would be infinite bubbly universes, where dark energy tears everything apart before anything forms. Infinite universes, where light travels too slowly. Infinite universes, where electrons are the size of footballs. Infinite universes, where everything is just as it is in our universe's physics. The possibility of a copy of you stems from the idea that there might be only a finite number of ways to combine all the matter in a universe. This idea is hypothetical, relying on our current understanding of quantum information. If this is true, and the ways electrons Quarks, neutrinos, photons, and dark matter can position themselves in any universe are indeed finite. Then in a multiverse with enough bubbly universes, each particle combination wouldn't just appear once, but many, many times. The landscape before time, legend has it. In the ancient lands of what is now central Turkey, there was a knot tied to an ox cart. This wasn't an ordinary knot. The legend had grown that anyone who could untie this knot, a knot so intricate, so intertwined, so complex that no one could figure out where it began or ended, would become king of all Asia. So when Alexander the Great heard of this, while conquering the Persian Empire, he very much wanted what the knot promised. There the knot sat, firmly tied, relentlessly fixed. As his followers watched, Alexander came up with a clever, simple, quick solution. He drew his sword and cut the knot. To modern theoretical physicists may not share much with Alexander the Great, but they did find their own Gordian knot and came up with an equally quick and brutal solution. String theory is a bold attempt to do two things at once. On one hand, it promises a quantum theory of gravity, which has been an unsolved mystery in physics since the development of the seemingly irreconcilable general relativity and quantum mechanics. For over a century, physicists, despite their best efforts, have generally failed to consistently bring gravity into the quantum realm, though string theory remains the most popular attempt. It also hopes to become a theory of everything through a set of simple equations describing our entire reality, explaining what the natural forces are and why they have the properties they do, while also explaining all particles in nature and why they have the properties they do. Ultimately, if string theory lives up to its promise, then if you have any question about fundamental physics, it will have the answer. String theory hypothesizes what we think of as particles aren't the fundamental units of reality, but vibrating loops. Different vibrations of the loops correspond to different particles, just as different vibrations on a guitar string correspond to different notes. But 3 dimensions aren't enough for these tiny strings to vibrate in all the ways needed to explain the vast array of particles we observe in nature. Therefore, string theory also hypothesizes the existence of extra spatial dimensions, either 10 or 11, depending on the theory. But all these extra dimensions are invisible to us. They curl up on themselves at the smallest scales, far below the detection threshold of anything we have, even though we have no evidence for these extra dimensions' existence. They are necessary for string theory, because it's within these extra dimensions that strings have the freedom to vibrate in all the ways they need. But this idea of curled-up extra dimensions has a not-so-small problem. All the extra dimensions of the universe can curl up on themselves in a vast number of ways. About 10,500 different options. Each option imposes a different set of restrictions on string vibrations, just as different guitar neck lengths change the types of notes the instrument can produce, because string vibrations are responsible for the physical properties we see in the universe, and the shape of all these extra dimensions controls how strings vibrate. Each potential way the extra dimensions curl up would produce a completely different universe with different particles, different forces, and different fundamental constants. We just don't know which universe we live in. Because we haven't yet understood the complex mathematics of string theory. We know the shape of extra dimensions determines vibrations, and vibrations produce particles. But we don't know how this all works. If you hand a string theorist a specific configuration of extra dimensions, they can't tell you what the resulting physics would be. String theorist Leonard Susskind called this the landscape. It's the collection of all possible configurations of extra dimensions. Each configuration leads to a universe with a completely different set of physical laws. This landscape is conceptual. It's a mathematical map of all possibilities. Our universe occupies one point in this landscape, just one point among 10,500 possibilities. To visualize this landscape, imagine walking barefoot through a vast field of rolling hills, sporadic rock outcrops, wooded clearings, tranquil streams, and placid lakes. As you traverse this field, each step samples a different patch. Maybe one footstep lands on soft grass, another on a mossy stone. Slipping, another plunging into icy water. But the landscape spread before you isn't just one universe, but a universe of possibilities, a mathematical structure containing all variations of universes possible. In string theory, each step represents a universe's realization, an arrangement of a universe, an arrangement of matter and forces, and radiation and constants. The lush hills to your right are a region where the cosmological constants value is small enough for life to survive. Beyond the mountain, gravity is too strong. The river's rapids are all universes where light speed is too fast or charge too low. Our universe is at one point in this landscape, a specific sample, where the universe's nature allows life to exist, where the configuration of extra dimensions allows string vibrations. That makes stars, galaxies, and us possible. But even if we did know how to link a configuration of extra dimensions to string vibrations, we'd still have no way to explain why our universe behaves in this particular way. Why did our universe choose this dimensional arrangement over any of the others? This arrangement seems to favor intelligent life's development, at least to our understanding. But most other arrangements might be too vast, too empty, too strange. Therefore, when string theorists began developing the landscape concept, they kept bumping into this annoying Gordian knot. Why did our universe's extra dimensions curl up in this particular way, and not any other? Is it just an accident, or is there a deeper reason? This is where eternal inflation could save the day. The landscape is a profoundly hypothetical idea, a plane of possibilities, mapping out every loud universe in string theory. But it isn't a place where new universes are born, nor a wider protocosmos. Yet eternal inflation and its implied multiverse, while also highly theoretical, are concrete physical entities. In other words, the multiverse could be how the string landscape manifests itself. Each new bubble universe could have its own set of physical laws, its own set of particles and forces, and its own forces for each particle and energy. Each of these bubble universes corresponds to a singular point on the landscape, and these universes are samples of possible configurations of extra dimensions, a single chord on a cosmic instrument, vibrating its own unique set of frequencies. But though the concept is enticing, Currently, the link between string theory and eternal inflation is tenuous at best. We don't fully understand the physics of inflation, assuming inflation is even the correct description of the very early universe. This means we don't know how deep the multiverse is, whether bubble universes only adopt familiar forces or different arrangements of particles, or whether they exhibit new configurations of extra dimensions, leading to completely new physics. But the link is attractive. Not only is our universe one of many, but across the span of creation, every possible melody arises, every possibility is realized. This also saves string theory from the seemingly impossible task of having to explain why our universe has the properties it does, why it has this particular curling of extra dimensions and not any other, by making every kind of universe, every possibility realized. We guarantee that we find ourselves only in universes with the physics that makes us possible. We are here at this point in the string landscape because we couldn't possibly exist anywhere else. Those universes are there, sampling every part of the landscape countless times, but they're almost all empty, lifeless. We are here because this is the only universe we can call home. This line of thinking is called the anthropic argument, that the universe is the way it is, because otherwise we wouldn't be here to observe it. So even though it's the ultimate conclusion of combining the string landscape and multiverse ideas many scientists consider, this line of thinking yields no useful result. We could never directly test the string landscape because according to the string landscape, we would always arise regardless. We can't say why our universe has this configuration beyond it being compatible with life. In response to this, some theorists attempted to ground the landscape on firmer footing. For example, using some simplified calculations derived from string theory, they hoped to be able to say the amount of dark matter, dark energy, or the electron's mass, or any other parameter that makes physics work the way we know it, is the most probable outcome in the landscape. This analysis wouldn't eliminate concerns about the anthropic argument, but at least would alleviate some worries about our particular universe being so special and fine-tuned. But of course, this is all highly speculative. We don't know how or if the string landscape relates to eternal inflation, but if it does, it offers a startlingly different perspective on our universe. And the Big Bang, before the Big Bang would be inflation, and before inflation there would be eternal inflation and the multiverse, and before all that there would be the string landscape, but not in the sense that the landscape is a physical entity. The idea is that before the possibility of universes, there was the reality of string theory and the landscape. With these rules, universes could simply continue evolving according to the mechanisms of strings and higher dimensions, mechanisms that manifested in the first inflationary event, starting the race toward diversity. From there, independent bubble universes began expanding and exploring, discovering every nook and cranny of all possible string dimensions. But this extension of thought, grounded in string theory within a multiverse or other physics we haven't yet dreamed of, brings us back to the ultimate question: why is there something rather than nothing? What created string theory, the landscape, What was before the Big Bang? If physical laws make our universe, the multiverse, the landscape possible, then why are there physical laws in the first place? Before you were born, there was a time. Before you were conscious, the universe still existed. Evidence is everywhere: your parents, memories and stories of older generations, photographs and monuments. These existed before your time. Your birth may be your beginning, but not the world's beginning. So could this also be the case for our universe? We've seen our universe might have ignited in a quantum fire known as inflation. And this inflationary event may not have been solitary. It could be part of an eternal inflationary chain, creating a grand cosmos that will forever keep inflating, and in the process unfurl a multiverse of possible bubbles. And this multiverse might, in the process, unravel the string landscape mystery, explaining why our universe has properties suitable for life and intelligence. But though inspired by decades of theoretical research, string theory remains speculative, with no experimental verification. In fact, because we lack the mathematical prowess to link extra-dimensional configurations to string vibrations, we actually can't test string theory despite its mathematical might. It hasn't yet met the challenge a proper physical theory must overcome, making experimentally testable predictions. Even eternal inflation, though still unsteady, is at least driven by the language of quantum fields based on our current physical understanding. Most cosmologists strongly suspect something like inflation happened in the early universe. This suggests there are other alternatives: the story of inflation, eternal inflation, and the string landscape isn't the only way. Staring into the gray mist behind our Big Bang. In 2001, for physicists Justin Cowrie, Bert Overt, Paul Steinhardt, and Neil Turok proposed a completely different cosmological model. One, still based on the latest thinking in string theory, but requiring no inflation at all. Before what we call the Big Bang in this model, our three-dimensional universe is a giant brain floating in the endless void of a higher dimensional reality. Unfortunately, we cannot access these higher dimensions because the particles constituting our reality are confined to living on this brain, so our universe only appears three-dimensional. Long ago, this theory posits before our Big Bang, our universe's brain was cold, empty, and featureless. But it wasn't alone. Other brains existed in the higher dimensional reality. At some point, another brain collided with our own. The brains met at a point, releasing a storm of energy and triggering shockwaves. From our perspective, this was like a Big Bang, a hot surge flooding the universe with particles and radiation at a single point. This is called *ekpyrotic* cosmology, from Greek for conflagration. The model can reproduce broad features of our universe, like flatness, lack of defects, the appearance of Big Bang expansion, even structure formation, without invoking inflation, and without constructing a multiverse. This apeirotic model also has the feature of being able to reignite the universe. Our brain could collide with another in that higher dimensional space again, restarting the process, igniting a new Big Bang. The single event we see in our past is like a ball bouncing on a floor, regular and repeatable, and the ekpyrotic model isn't the only one claiming we live in an endless grand cycle, another approach to solving the mystery of combining gravity with quantum mechanics, called loop quantum gravity, suggests the smooth, complete space-time structure we see is actually a series of discrete elements like pixels on your computer screen. In our classical understanding of cosmology based on general relativity, the universe began from a singularity, a point of infinite density, but in loop quantum gravity, there is no such thing as a Big Bang. When trying to compress matter, space, or time into a region smaller than reality's fundamental pixels, a pressure-resist collapse. Just like a spring gets harder to push the smaller it gets. So when the universe collapses on itself, it reaches a point where a natural quantum rebound flings it outward, overturning the appearance of a singularity, igniting a new Big Bang. There are even more models and ideas, allowing the creation of new universes, like Roger Penrose's conformal cyclic cosmology. In this model, the extremely distant future universe becomes so thin, cold, and dispersed that space and time become meaningless, opening the possibility for a new Big Bang. Therefore, regardless of the situation, the answer to our Big Bang's origin, whether through inflation, string theory, loop quantum gravity, or something more exotic, lies in the realm of quantum gravity. We must understand how gravity operates at extreme scales to delve deep into our own past. Understanding our universe's origin, we know the general relativity singularity, the infinitesimal point at our universe's beginning, is wrong. It just shows our mathematics is breaking down. We need new understanding. This new understanding might even require rewriting the definition of time itself. Our concept of the universe includes not just particles and radiation, but forces and interactions, and the structure of space-time itself. Of course, we can conceive of a beginning of space, an imaginary spark that made space appear and unfurl, becoming the cosmos we see. But the beginning of time, before time existed, how could there be causality? How could our universe's clock start before the clock came into being? The universe's beginning includes all its features, including time itself. Thus we can push the universe's starting point beyond the edge of the Big Bang into the realms of eternal inflation and the string landscape. But even in these most advanced and hypothetical ideas, there's still a beginning, a moment when time began. If this sounds like a paradox, it's because it is. Much about time is something we currently don't understand, and may never understand time. Then what can we do? Our concept of time in physics is already messy and contradictory. In quantum mechanics, time is treated as an external parameter, a fact of the universe's uniform forward march that allows observers to make observations and interactions to happen. In general relativity, time is fluid, relative, and tied to space through the fabric of space-time. To understand the cosmos, we must reconcile these views. Very simply, we can't confidently talk about a moment asterisk before asterisk until we can confidently understand what time even is. Therefore, currently, our thinking about space and time isn't sufficient to resolve the beginning of it all, because terms like beginning are so ingrained in our biological existence, so rooted in our basic conscious awareness of the world around us, that we may be unable to escape our bias, even when extending it to the farthest reaches of our most advanced theories. In reality, in the early universe, the progression of time, the separation of past, present, and future, might break down. Conditions might become so extreme that the separation of before and after could lose all meaning. Causality might become scrambled at the universe's earliest moments. This might ultimately be futile because time itself, at least the way we currently understand it, would become a useless framework to organize the cosmos. Even if we could overcome all these difficulties, this still wouldn't be the end, because whichever theory we propose to explain our own origin, whether an infinite multiverse chain, colliding brains, or endless repeating Big Bang cycles, there still is rather than isn't. There are still physics, still rules, laws, and ordered harmonies allowing the universe to exist. If it's inflation, then there are quantum fields. If it's colliding brains or the landscape, then there are strings. If it's loop quantum gravity, then there are discrete units of space-time. Our exploration of what came after the Big Bang's beginning will undoubtedly reveal more rules, more structure, more laws. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries, and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.